All right. Did you guys do some problems? Maybe? Hopefully? Okay. So let's start with finding the internal loads at the center of this guy. Okay, so we'll just say it's right in the middle. Okay, so go ahead and find me the internal loads at C. Get you warmed up.
Are we moving on to the next lesson today?
Yeah, we are moving on to the next lesson, but I want to make sure you can do this one before we move on to the next.
We're trying to find the internal load at C.
Yep, find the internal load at C. Guys got some numbers?
Not yet.
Anybody got reactions?
Well, yeah. Oh, yeah.
What do you have for reactions?
CY is 53.3, or I mean BY is 53.3, and AY is 23.3, negative 23.3.
AY is negative 23.3. Anybody else get that? Yeah? Did you get equations that look like this? Okay. It's all right. If you did it from the other way, your equations would look different. Anyone do it from this way? Anyone look at the left side? Everyone did it from the right? Oh, don't be afraid of the couple moment, guys. Nothing to be afraid of there. Oh, yeah. I understand. I thought about doing that too, but I thought, no, I won't wimp out. I'll do it this way. Someone's going to slog through it with me, but nobody did. Okay. What'd you get for the moment? Looks like I'm going to go with like 195 foot-pounds. Is that what you guys got? Yeah? Brandon did. Anyone else? Mitchley says yay. Okay. So here's the challenge, right? The reason we're trying to determine what the internal loads are is we want to know where they're at a maximum and a minimum. Because that will tell us how big we need to make our beam, right? Because we need to counteract the highest bending moment and the highest shear force. So do you think that point C is the point of maximum bending moment? I don't know. I can't look at this and tell, right? Seems unlikely to me since there's 300 foot-pounds here, but I don't know. It could be, it could not be. I really don't know. So the answer to doing this is we need to plot. We need to make a graph of how the bending moment and the shear force changes, okay? And the way we do that is we look at areas where, say, let's look at shear stress first, okay? So there's no change in load in the first 3 feet, right? So if you do this with me, if you think about it, what would the shear stress be right here? What would it have to be? It'd have to be 23.3 pointing down, right? Does everyone see that? In order for this to be in equilibrium, we need 23.3 pointing down. How about if I move over? What would it have to be now? All the way till here, we don't know. Something might change. Okay? So what we need to do is to divide the beam into 3 regions. And those 3 regions correspond to, are the boundaries of each region, I should say, are where there's a force application. Okay? Because that means something's going to change. All right? And then we look at each of these 3 regions. We start from the right and we go to the left. So we'll draw a free body diagram. Okay? So here is, let me make this clear. Here's region 1. Its free body diagram looks like we have 23.3 going down. We have shear pointing down because that's would cause clockwise rotation. We have a normal pointing out of the cut, and we have a bending moment making a happy beam. Okay? And I'm going to put this cut an arbitrary distance x from the left-hand side. Okay? Now we write our equations of equilibrium. So I'm going to say sum of the forces in the y has to equal 0. Okay? So it looks like in the y I have negative 23.2 minus v equals 0. Is it 23.3? Sorry. Okay. So that tells me that v is equal to negative 23.3 pounds. And that's good from 0 to 3 feet. So this is the range 0 to x to 3 feet. And if I sum my moments, about the cut counterclockwise, they have to equal 0. So here it looks like I would have my moment, m, plus 23.3 times what? X, right? Because the lever arm from the cut to the 23.3 is x. Okay? That will have to equal 0. So the moment in this area is going to be equal to negative 23.3x. Okay? So I'm going to leave myself some space so that we can do regions 2 and 3. But I'm going to come down here and I'm going to make a plot. So here's my beam. Here are the loads on the beam. Okay. And I'm going to make a plot that goes from the left end of the beam over to the right. And next to it, I'm going to put a V. And I'm going to do the same thing right below that, though you can't see it. I'll move it in a minute for the moment. Okay? So as we go across, that's the x-axis. For the shear, this is in pounds. The moment is pound-feet. Okay? So this tells me that if I go back up to my equations for region 1, it says from 0 to 3 feet, I have negative 23.3 pounds. All right? So I'm going to come to here, negative 23.3, 0 to 3 feet. Okay? For my bending moment, I determined that I had negative 23.3 x. Okay? So that means at 0, I'd have 0. And if I go to 3, I'd have 3 times 23.3, which I think that's 70. Yeah. Right? 3 times 23.3 is going to be 70. So I'm going to put a dot right there at 70. And what type of line is negative 23.3x? Yeah, it's a straight line. Okay. So what I have is a straight line, constant slope down. Okay. So let's kind of go back through the steps. First thing I did is I divided it into regions. Wherever there's a load applied or a change in the load condition, that's a boundary for a region. So here I have 3 regions because I have 2 loads, right? So I look at the first one that's from 0 to 3 feet. I draw my free body diagram where I put the cut at distance x from the end. Then I sum my forces in the y, and I figure out that my shear force is constant throughout that area. It's 23.3. And I find out that my moment is has a straight line down of negative 23.3. Okay? Sorry. All right. So next, let's look at region 2. Okay. I'm going to sum the forces in the y direction. Looks like I have negative 23.3 plus v, sorry, minus v equals 0. So again, we have v is equal to negative 23.3 pounds. Okay. So I can come down here to my chart, negative 23, and I'm going to go up another 3 feet to 30 pounds, because this is for 3 is less than x is less than 6, right? The region that we're doing here.
So on the V graph,
Yeah.
the x is feet, or is it distance?
Yeah, this is always the distance across the beam for both of them. Say that again?
So you drew region 2, but you went from 0 to 6, not 3 to 6.
Got it. So Liana's pointing out, how come your free body diagram is from 0 to 6, but you're saying these equations are only good for 3 to 6? Is that what your question? Right. That is your great point. So while these equations are only good for this region, in order to think about if we were finding the internal loads for this region of 3 to 6, we'd have to draw a free body diagram like we did over here, right? So we have to include the end pieces. So remember, all we're doing really is we're trying to make a plot from one end to the other. So we're trying to find what the internal bending moment or shear stress is from 0 to 9 feet here, okay? And what we're saying is that it will be there's no change in load condition as I go from 3 to 6. So if I draw the free body diagram as I've done here, where the cut is some distance x, right, from the end, then I can determine what those equations will be just in this region. Right? So the equations are only good for the 3 to 6, but in order to find them, I have to use the 0 to 6. Yep. Okay. So now let's sum the moments about the cut. Okay. So moments about the cut, let's see, we will have 23.3 times x, right? That's the distance from the cut. And we're saying this way is positive, so that would be positive. We'll have minus 300 foot-pounds plus m equals 0. Right? Because I'm looking here, I sum the moments about the cut. I have 23.3 times x. I have 300 foot-pounds. Why don't I have to use the lever arm with my 300 foot-pounds? It's already a moment, okay. It's a couple moment, right? So a couple moment says that there are two forces separated by some distance that are equal and opposite. So it wouldn't matter whether those two forces are here or there or here or there or there, right? It doesn't, because they already have, I see confusion in some people's eyes about this. So let's take a little bit of a detour here, okay? Okay? You're happy about this detour? Are you happy about this detour, or you're saying you just always look confused? That's your natural state. Got it. Okay? So let's say I've already done my work, and I know that there's 300 pounds up here, and that I have a couple moment right here of 100 foot-pounds. Okay? And I'm trying to find my internal loads. Like this.
Is a couple moment something where, like, oh, there's, you know how there was couples of forces and then you derive it into like a moment? Is that kind of what the couple moment is representing?
Sort of. So let's take a couple moment is like when we were doing force simplification, absolutely. So an equivalent beam might look like this. Not exactly. Moment and torque are not exactly the same thing. They can be used interchangeably, like in physics, they might use them interchangeably, but yeah. Okay. So this 100 foot-pound couple moment here, we could break into two 50-pound forces that are equal and opposite and separated by 2 feet. And let me show you that where these guys act on this beam doesn't change what the internal moment is, right? So let's take, for example, let's say it's 3 feet to the first one, okay? So I'm going to sum my moments about the cut. All right, so summing my moments about the cut, I'll have 300. Oh, I guess I have to give you a distance here. Let's say it's 8 feet. So I have 300 times 8, right? And that's going to be negative. So I'm saying counterclockwise is positive. Then I'll have plus 50 times 5, right? Because 50 here is 5 feet. Minus 50 times 3 plus the moment equals 0. So look right here. What's the net? If I put this in parentheses and I had you evaluate this first, how would you evaluate it? Would you maybe do something like 50 times 5 minus 3? Which I think that's 2, so you'd end up with 50 times 2, right? Which I think is 100 foot-pounds, right? Which this and this are the same. Okay?
So those two are always going to be 2 feet apart?
Well, what I'm saying is you're given a couple moment. that it's 100 foot-pounds. They could be 1 pound each, separated by 100 feet, right? They could be 100 pounds each, separated by 1 foot. But it doesn't matter. What matters here is that the forces are equal and opposite, so they counteract each other, so they don't affect the shear. And the fact that this is applied 3 feet away, actually it doesn't matter. Let's change it to 5 feet. Okay, if that's 5 feet, then I need to change this to be 7 and this to be 5. 7, 5. We still have 50 times 2. It's still the same thing. Okay? So the nature of a couple moment is that it doesn't matter where it's applied. It's just that it is applied. So you don't need a lever arm here. The couple moment, the fact that it's a couple moment, is already accounting for the lever arm. It's saying that there's 2 forces equal and opposite separated by some distance. Okay? So you don't need to multiply. When you see a couple moment like this, you don't need to worry about its lever arm. All right? So let's go back to this. We found here that we have 23.3x minus 300 plus m equals 0. Or I can rewrite that the moment is equal to 300 foot-pounds minus 23.3 times x. Right? And that x, it's important to remember that x starts at the end of the beam at 0. Okay? So let's figure out at 3n, we'd have 300 minus 70. Right? Because 23.3 times 3 we decided is 70. So 300 minus 70 would give us a value, I'm not going to beat a scale here, of 230. Right? So it'd give me a value of 230. I didn't leave myself enough room, so I'm not exactly to scale. And then what happens, what's it going to be at 6? Right here at 6. So at 6, I'll have 23.3 times 6. Well, if times 3 was 70, that'd probably be negative 140. So 300 minus 140 would give me, I think, 160. Does that sound right? So hard to do without it to scale, but we'll say we're right here. Okay? So here's 230, here's 160, here's negative 70. Okay? So let's go back to region 3. Any questions actually so far?
So you just find it at the endpoints. So like in, you want to say like we're trying to do from 3 to 6, so plug in 3, see what you get.
Yeah.
Plug in 6, and then just draw lines.
You could do it. That's how I happen to do it. You could just plot this line if you wanted, right? Or you could say, I know the slope of that line is negative 23.3, and I know that I start at 230, and I'm going to go over 3, right? So 230 minus 3 times 23.3 would be 230 minus 70, 160. Okay? All right, so let's do the last region. So the last region, I've got 23.3 down. I have 300 foot-pounds of twisty. And I have 30 pounds down. I'll have my shear and my bending moment. And the cut is still at X. Okay. This is at 6, right? So what would the distance from the cut to the 30 pounds be? If this distance is X, this distance is 6, what is this distance right here? Exactly. this would be x minus 6. Okay. So let's sum our moments, sum our forces in the y. We'll have negative 23.3 minus 30 minus v equals 0. Or that tells me v is equal to negative 53.3. Okay, so I come to my chart. I can come down to negative 53.3. Look at that. Here I have 53.3 acting up. Okay. So this is my shear diagram, and I like to shade, okay, because it's helpful to have it shaded. Now let's sum our moments. We're going to sum them about the cut.
Are we going to find the area eventually?
Mm-hmm.
So we're going to start using integral.
Maybe. Sum the moment about the cut. All right, so what do I have happening about the cut? Looks like I have 23.3 times x minus 300 plus 30 times x minus 6, right? That's what we decided the distance from the cut to the 30 pounds was x minus 6, plus m equals 0. So it looks to me like m would be equal to negative 53.3x plus 480.
So we don't include the 53.3 end force because it's just an x, so we don't know if it's at the end.
So the question is, in the shear, we don't include the 53.3 that's on the end, and that's correct because we're just looking at the region, right? This would be the end of, this would be the boundary of another region. So we're looking at the area that's between 30 pounds and the 53.3 at the end. So we're saying what's happening in here. It's a lot like in calculus when you were kind of talked about limits. As you approach it, get really, really close to it. That's what we're doing. As you approach, get really, really close to that, what's happening. Okay? So now we can plot this. Remember that x is at 6 here, right? So could someone figure out what 480 minus 6 times 53.3 is? It's 160, okay? We have a slope of negative 53.3. So could you figure out then what 9 times 53.3 is? So we're going to be at 0. And here is our moment diagram. Okay. So when we started this problem, right, way back up here, we found the bending moment at C, and we found it to be 195 foot-pounds. Is that the max? It's not even close to the max, right? The max is 230. And we also found our shear, right? We found our shear was negative 23.3 pounds. Is that our max? No, the max is more than double that, okay? So these are critically important for designing the beam because now we know that our maximum bending moment is 230 foot-pounds and our maximum shear stress is 53.3 pounds. Okay? So drawing shear and moment diagrams for beams is critically important. All right? Let's do one more together before I have you do one on your own. Okay? Anybody want to help me with the reactions? Okay? How many regions do I have? Why are there 3, Liana? Sure, 3 different regions where the load is constant is what we typically say. Okay? All right, so let's look at region 1 then. Can we do this by inspection? Can you just look at that and tell me? What's the shear going to be? What's the bending moment going to be? Positive or negative 500x? Maybe we better do this one. Sum the moments about to cut. I'll have m minus 500x equals 0. So m is equal to 500x. Right? Okay. Everybody follow that okay? Let's do region 2. What's the shear? Why is it 0, Joseph? V plus 500 minus 500 plus V, that'd be 0. Okay? The moment then? Be x minus 5 there. So I'm going to have to write this one out. Sum of the moments about to cut. Set it equal to 0. I'm going to have minus 500x plus 500x minus 5 plus m equals 0. Right? That looks like m is equal to 2,500. Huh. It's constant.
Oh, because it's like you were
Mm-hmm. Okay. And lastly, let's do region 3. What's the shear going to have to be? Negative 500. Right? Because we have 500 up, 1,000 down, then we need another 500 up. So it's going to be negative 500 there. The moment?
So with each section, we're just adding on. I thought we were like splitting it.
Yeah, so the question is in each section we're just adding on. We're not splitting it. And that's correct. We split it into regions where the equations apply, but to develop the equations, we need to look at the whole thing. Right? So I can't see the moment here, so I'm going to have to do, I believe it is, but let's go through that. So I'll have minus 500x plus 500 times x minus 5. Yep. Plus 500 times x minus 10 plus m equals 0. So negative 500x and 500x here cancel. And I end up with negative 2,500 plus 500x minus 5,000 plus m equals 0. So m is equal to negative 500x plus 7,500.
So can't you just take the last part and then add in force?
So the question is, can't you just take the last part and add in the new force? Sort of, but it's just as easy to just do it this way and make sure you got them all. Okay, so let's plot these. Oh, shoot. Oh, we're back. Never mind. Okay. So let's plot. Here's my shear. Let's divide it into thirds because we know we have 3 regions. In the first region, V is 500. Okay. In the second region, V is 0. And in the third region, V is negative 500. Okay. Let's look at the moment. The first region, it's 500x. So that means we start at 0 because 0 times 500 is 0. And we go to 500 times 5, which is 2,500. In the second region, it's constant 2,500, so we just draw a straight line across. And in the third region, it's a slope of negative 500. And if we wanted to make sure that we start at 7,500, we could realize we're 10 across. So 10 times negative 500 would be negative 5,000 plus 7,500 would give me 2,500. So indeed, what happens is I come back down and I go to 0. Okay.
We didn't need the end force, the one on the right side.
So the question is, we didn't need the end force, the 500 on the right side. No, because what we're doing is we're developing the equations that go just between the loads, right? So you can see there, it's kind of discontinuous here where the loads occur. Same thing at the end there. It's discontinuous.
For moment, after the, like at the end of the second section, wouldn't it be at 7,500 for the graph?
You're asking, should it be at 7,500 here?
Yeah.
No, because remember in section 2, which goes from 5 to 10 feet, we found it was a constant 2,500 foot-pounds. So it's just a straight line across at 2,500. Then the 7,500 pounds that we have, that's just the y-intercept for that line that starts at x equals 10 and goes to x equals 15.
Oh, so if like the line were to keep going, it would...
Yeah, that's telling you that way up here,
Oh, yeah.
right? Okay? How you feel about this? So? Okay, let me give you one to do. Does it matter which side you start from? No, you can't switch sides halfway through, and tradition is to start from the left and go to the right. Because your graph kind of starts from the left and goes to the right. You know, if you started from the right and went to the left, you'd have to have positive x to the left, which just, I mean, that's like being left-handed. You might as well just not even try. I'm just kidding. I'm sure in a class this big, there has to be someone left-handed. What's glorious is that I don't know who that person is, so they can't feel like I was personally insulting them. I was just insulting everyone who is left-handed. Brendan, are you left-handed? Oh, sure seems like you are. Oh. Oh boy, I just cracked myself up. Ooh, that's a good one. I'm gonna remember that. Need some ice for that burn.
Like if I tried to draw, it's a different story. Are you drawing for fun and then you draw for math class? Or just actually?
All right. How many regions do we have? Yeah, so we're going to have a normal here, right? Some AY and some BY. So it looks like here's one region, here's another region, and here's another region. So we're back in, we have 3 regions again. 1, 2, and 3. Okay? So I'm going to pause this, and I want you to draw me a shear moment diagram. Okay? I should give you some distances. Fair point. Okay? I'll go ahead and give you a distance of 5 here, 5 here, and 3 there. Okay? Now I will pause it and you will go. All right, I think you should end up with some charts that look like this. Okay?
Can you show us how to do the it might be a little bit
Sure.
different.
So let's do in region 1, the moment equation. Did you have 380? Okay. You good?
I'm not good. Speak for yourself, please.
Okay, so if I'm doing for region 1, sum the moments at the cut should be equal to 0. This distance is x. So I'll have negative 380x plus m equals 0, right? So m is equal to 380x. So that means I start at 0. If I go across 5, I'm at 1900. Region 2, right? In region 2, I would have negative 380x plus 700 times x minus 5 plus m equals 0. So m then is going to be negative 320x plus 3,500. Okay. And then the last region we'll have 380, 700, 220. Right? And so that'd be 380x minus 700 times x minus 5. Sorry, that'd be negative 380 plus 780 minus 220 times x minus 10 plus m equals 0. And that'll get us something like negative 100x. M is equal to negative 100x minus 35 or plus 35 minus 2200. I think that's plus like 1300 or something like that.
Can you explain like visually how like why you would add like the -5 and the -10?
Yeah, so the question is, can I explain visually why the -5 and the -10? I sure can. So we know that this distance is x, right? It's our unknown. We know that this distance is 5 and that this distance is 10. When I'm summing moments about the cut, I want to know what this distance is, which if x is the whole length and I take 5 away, that gives me this distance. So this distance is x minus 5. And same thing here. If I know the whole distance is x and this is 10, then the distance of the 220 from the cut would be x minus 10, which is this distance here. Okay. All right. Okay, so we only have a few minutes left. I want to make sure that I cover distributed load. So let's do one simple beam. And I'm going to put a distributed load on it. That goes halfway across. Okay, and we'll give this 100 pound per foot. We'll say that it's 5 feet long. And this is 5 feet. Okay. So the reactions then, let's see, AY, BY. AY plus BY is going to have to be equal to 500. And it's going to be 1/4. So AY is 375 and BY is 125. Okay, so I'm just doing those in my head because we have to do them kind of fast so that I can show you this example. Okay, so I think those are correct. If they're wrong, you can work it out later. How many load regions do I have? 2. Exactly right, Liana. Where are they? Yep. One here and another here. Okay. So let's draw the free body diagram for region 1. Egads. What's going on with this?
So you have to put it into one force in the middle.
Yeah. So we're going to have to sum the forces in the y and set them equal to 0. So what's happening in the y? Well, we have 375 going up. We have some part of our distributed load. So if we wanted to figure out how much this is, how do we figure out if we have a distributed load what its resultant is? Yeah, it's the 100 pounds per foot times the number of feet, right? So in this case, that's x. So we have 100 times x, and I should change this to be down, right? It's not plus, it's down. So minus 100x minus v equals 0. Or v is equal to 100x minus 375. I have that backwards because this is negative. So it's negative 100 plus 375. Sorry. So it's 375 minus 100x. Okay. What about our moment? And I have to sum the moment about the cut. Counterclockwise is positive. So I have negative 375 times x, right? And what about this guy? It's rectangular, so we know that its resultant acts in the middle. But so first we need to figure out what the magnitude of that force would be. So it's going to be helping us, or it's going to be in the positive twist direction. And the magnitude of the force would be the 100 times x, right? That gives me the resultant. Then I need to figure out its distance from the cut. Where would this guy be in relation in terms of x? 1/2 x, or x over 2. Right, so this is force times distance to get the moment. The force is my 100x. The distance is my x over 2. Nope. Okay. So the moment is equal to negative 100x squared divided by 2 plus 375x. Snap. The 100 over 2 does simplify, yes. Thank you. It's 50. Negative 50x squared plus 375. Is that a straight line? It sure ain't a straight line. Okay? So we're out of time. What I wanted to show you, though, was this distributed load guy. You slice it the same way. You just have to be cognizant of the fact that your resultant here is going to be equal to 100x. It's the depends on how far away you are, how much that load will be. So what that's telling us is that our shear is changing as we go from 0 here across. It changes from 375, and it gets less and less as you go across. Okay? And then when it comes time for the moment, you have to, again, consider that if I take the moment with half of it sliced, that's going to be different than taking the moment with all of it sliced, because the magnitude of the force and its distance are both changing. And so that becomes a square. All right? I have posted your homework. Your homework is to first by hand calculate in 2 different spots on a beam the internal loads, and then second to prove that you have it correct by plotting the shear and moment diagrams. All right? You have a 4-day weekend, 3-day weekend?
3 days.
You have a 4-day hiatus from statics, right? So I'll see you next Wednesday. And our midterm is a week from Monday. Okay?